Now that we've done the standard stoichiometry problem and practiced a few examples of those, I'm going to do a non-standard stoichiometry problem. It's a pretty typical type problem, but there are more moving parts in this one than there were in the first one. This is one of the higher numbered end of chapter problems. We're going to work on problem 3.105 out of the Brown and LeMay text. And as always, we're going to quickly take a look at the text of the problem. So here's what it looks like. As you can see, there are a number of parts to this thing, and there seems to be more going on than just a standard stoichiometry problem. So we are going to dissect the problem and then go ahead and solve its parts. And as always, to put ourselves in mind about doing work like this and getting ourselves centered and ready to go. For me, I usually want to think about things like kittens and puppies. So for a moment, let's contemplate that. Okay, now we're ready to start tackling this problem. You will notice that in the first part of the problem, they tell us about a chemical equation. They don't give us the equation itself. They just expect us to write it out and balance it. We note that it's a combustion reaction, meaning it's a reactant reacting with oxygen. And so it's going to be a pretty straightforward type thing. For this particular reaction, it's acetylene. They tell us we have a mixture of acetylene, C2H2, in the gas phase. And it's going to combust, which means react with oxygen. And remember, for a carbon-hydrogen containing compound, the products of a combustion reaction are always carbon dioxide and water. And almost always that's going to be thought of in the gas phase. And I'll even mark the oxygen out of the air in the gas phase. So there is the chemical equation. Now, of course, we can't do anything in the world of stoichiometry until we have it balanced. So we're going to go ahead and do that now. Starting with the simplest atom, I'm looking at my carbons, 2 here, 1 there. That's pretty easily corrected. All right, so now I have 2 carbons. Now, looking at the hydrogens, 2 hydrogens here, 2 hydrogens there. Ooh, the hydrogens worked out just fine. Now, onto the oxygens. 2 oxygens on the left, 4, 5 oxygens on the right, even odd number situation. So what I'm going to do is I'm going to write that in as 5 halves for the moment. That gets me a fraction, which we are going to clear out, but it does get the thing balanced. Now, to get rid of the fraction, what I'm going to simply do is multiply all coefficients in the equation by 2, the denominator of the little fraction I threw in there. And so that gets me a 2 here. That gets me essentially a 5 there. It gets me get rid of that one for a second, a 4, and gets me a 2. Now, making sure that everything is working out, I have 5 times 2 is 10 oxygens on the left, 4 times 2 is 8, plus 2 more is 10 oxygens on the right. Yep, everything is balanced now. So here's our balanced chemical equation. Now we're ready to start tackling the problem. The way the problem is written, we have 10 grams of acetylene, 10 grams of oxygen in a mixture, and they're going to ask us ultimately how much carbon dioxide and how much water we're going to make. And I'm going to worry about the carbon dioxide first. Classic stoichiometry problem, balanced chemical equation, an amount of something, question about the amount of something else in a reaction. But we also notice we're given information about 2 of the reactants here, 10 grams of each. This is, of course, a limiting reagent question. One of these, we're either going to use up all 10 grams of acetylene before all the oxygen is gone, and so acetylene will be our limiting reagent, or we're going to use up all 10 grams of the oxygen and still have some acetylene left over as we produce the carbon dioxide and water. So one of these is a limiting reagent, and therefore only one of the possibilities will produce the answer to the question, how much carbon dioxide can you make? There's a couple of ways of approaching a limiting reagent question. To be honest, I think the most straightforward way for students, particularly if they haven't done a lot of these in the past or they're just learning how to do it, is to simply do the stoichiometry problem twice. Figure out how much carbon dioxide 10 grams of acetylene could make in this reaction, figure out how many grams of carbon dioxide, 10 grams of oxygen can make in this reaction. Look at the two numbers, compare the two, and choose the one that produces the smallest amount of product. So here we go. That's what we're going to do, running the stoichiometry problem. As always, we begin with the 10 grams of reactant. And our first step of all stoichiometry problems, turn whatever you're given into moles. So grams of C2H2 are now going to become moles of C2H2. And as always, the gram to mole conversion factor is the stuff right off the periodic table, the molecular weight. And so 12, 24, 25, 26 grams per mole for acetylene. Step 1 of the stoichiometry process. Step 2, moles to moles. Moles of acetylene is going to go down here. That allows me to cancel them off. Moles of carbon dioxide up here. The numbers that go in here are always the coefficients of the balanced chemical equation. The 4 here, there's a 2 there. Pretty straightforward. Third step of all stoichiometry problems, moles of your product become grams of product. Once again, we need the molecular weight. For carbon dioxide, it is 44 grams per mole. And so now we do the magic calculator dance. 10 divided by 26 times 4 divided by 2 times 44. And what do we come up with? 33.8 grams carbon dioxide. Now, I'm going to make a note on here from C2H2, okay, from the acetylene only. Okay? That's how much we would make if we used up all the acetylene. So figure out which one of these two is the limiting reagent. We're going to run the exact same process again, this time around, starting with my 10 grams of oxygen.
And the same 3 steps are going to apply with just a few different numbers. I need grams of oxygen, moles of oxygen. 1 mole is 32 grams for O2. Mole of O2 becomes a mole of CO2. And the balanced equation says there's 5 moles of oxygen for every 4 moles of carbon dioxide. Moles of CO2, grams of CO2. 44 grams per mole. Do the magic calculator dance here. 10 divided by 32 times 4 divided by 5 times 44. And what do we get?
11.0 grams CO2 from the oxygen. Two different numbers, quite different from each other. Of course, the proper answer is this one. When we're doing this type of thing, figuring out which one is the limiting reagent, we always pick the reactant that produces the smallest amount of product. This implies that the oxygen has run out after producing 11 grams of CO2, so not all of the acetylene has been consumed, only some of it, not all of it. So the answer to part of the question here, how much carbon dioxide is this reaction mixture going to produce? 11 grams of carbon dioxide. Okay? Oxygen is our limiting reagent. Let me write that down too. Oxygen is the limiting reagent. And so that answers the first couple of parts of this problem. Okay? We've written the equation and balanced it. We've figured out which one is the limiting reagent. Part C is the one where most of the meat of the problem is. Here they want us to say, okay, when the reaction is all done, how many grams of everything? Grams of carbon dioxide, grams of water, grams of oxygen, grams of acetylene, how many grams of everything are in this reaction mixture? Okay? And so we're going to need to write down, the number of value for the C2H2, for the oxygen, for the carbon dioxide, for the water. Now, at end of the reaction mixture. Okay? Now, a couple of these we already know. How many grams of carbon dioxide are there going to be? Right there, 11 grams, 11.0 grams. And we know another one. How much oxygen is left? Remember, oxygen is the limiting reagent. That's the one that runs out. There is no more oxygen in this reaction mixture when the reaction is done, when we're at the end. So those two we already have answered. We need to know the number of grams of water, the other product in this reaction. Guess what? We're going to have to do another stoichiometry problem. Away we go. Of water. We got that one now. 2.75 grams of water when the reaction is done. So 11 grams of carbon dioxide, 2.7 grams of water. The last one they want then is how much acetylene is left over. We used up some of it. We don't have 10 grams anymore. Some of it's been consumed. But how much and how much is left? Now to do this one, we're actually going to do a bit of a trick. Okay, not really a trick. It's pretty straightforward in that we recognize conservation of matter. That we started off this process with 20 grams of stuff total. We used up all of this one, some of that one. But when conservation of matter says if you start with 20 grams of stuff in a reaction, you're going to end with 20 grams of stuff. It could all be product, or it could be a mixture of product and unreacted reactant. In this case, there is going to be some leftover acetylene. But the total amount of mass in this thing at the end must add up to 20 grams. Okay? So we have 20 grams of stuff total. And that's true at the beginning and at the end. Now, of those 20 grams, we subtract off how much oxygen is still in there. None, so that's pretty easy. We subtract off how much of this stuff is grams of carbon dioxide. Okay? That's pretty easy. We already have that down. We subtract off how much of it is the water. I'll just label that CO2, water. Okay? And therefore, when we do the subtraction here, we're going to get a 6.75 grams of C2H2 left over. And that's the last number we need, 6.75 grams of C2H2 acetylene left over. So we used a little over 3 grams, 3 out of the 10. We have 6 and nearly 7 grams left over when the reaction is done. And that answers all the parts to problem 105 out of the text. Okay? We had the words, so we had to write the equation and balance it. Okay. We recognize, because we have information about both reactants, that this is a limiting reagent problem. And in fact, in part B, they come right out and say, which one is the limiting reagent? We did the stoichiometry problem twice, saw which reactant, the oxygen, produced the smallest amount of product. That identified the limiting reagent and told us how much of that product we're going to make. And then they asked us to talk about the amount of water, the amount of acetylene, and the amount of oxygen left. Oxygen was our limiting reagent, so there's none left. And one more stoichiometry problem got us water, and then just using conservation of mass got us the remaining amount of acetylene. Relatively straightforward when it comes right down to it. So think that one over, practice a few on your own, and talk to you later.